In this video, I'm going to explain simply and clearly what a Hermitian matrix actually is. And to do that, you need to understand two fundamental ideas and then put them together. The first fundamental idea is that of the complex conjugate, which is actually extremely simple. So if we have a complex number, let's say the complex number z, and that's a plus bi. A is the real part and bi is your complex part because it's got an I in it. If you want to find the complex conjugate, all you need to do is switch the sign in the middle. So the sign on your I term just switches. So we've got the complex number z. If we put a bar on the z, that becomes the complex conjugate. And likewise, if you had a complex number that was a minus bi, you can get the complex conjugate by switching the minus to a plus. So simply change the term in front of the coefficient of I, and you get the complex conjugate. We can look at what this looks like in terms of matrices and find a matrix's complex conjugate. So if we had a matrix that looked like this, you could simply find the complex conjugate by changing all of the signs. Any real number's complex conjugate is just going to be exactly the same number, because this would be like 1 plus 0i, which would become 1 minus 0i, which doesn't really change anything, so you just ignore the 0i part. And so if we find the complex conjugate of this, we can say we've got a matrix M. The complex conjugate of M is simply going to be the 1 and 1 is going to be unchanged. This minus becomes a plus. This plus becomes a minus. Really very simple. The next really simple idea is the transpose. This shouldn't be difficult. Transpose is just where rows become columns. For example, if you have a matrix 1, 2, 3, 4, you just switch your 1 and 2 becomes a column here, so your row becomes a column, row becomes column, and that is a transpose. Now, let's put these two ideas together, and this is where the idea of the Hermitian comes in. So we've got what's called the conjugate transpose, which is also called the Hermitian transpose. So if we had a matrix M, which is defined as 1i minus I and then 1, we could find the complex conjugate of that matrix. So we just switch I to minus I and then minus I to I. So we just switch the signs of those. Then we find the transpose. So this row becomes a column. This row becomes a column. We now have the complex conjugate transpose. So we've got transpose here, complex conjugate transpose. You could, of course, do this all in one step. And that is your Hermitian transpose. You find the complex conjugate and then you transpose that, and you can represent that by M dagger or MH. Sometimes you'll see it as star, but that one's best avoided because it has some ambiguity in it. Personally, I would always use one of those two notations. And this brings us to the fundamental definition of what a Hermitian matrix actually is. A Hermitian matrix, A, is Hermitian if and only if your matrix A is equal to the conjugate transpose. And you can see that in this case, this matrix is going to be Hermitian because the matrix is equal to its complex conjugate transpose. This matrix and this matrix are exactly the same. So if you find the conjugate, then transpose it, and you get exactly the same matrix back. That tells you that it is a Hermitian matrix. Another really key thing that's worth remembering is that all real symmetric matrices are Hermitian, absolutely every single one. So for example, if you had this matrix, you can look at it, you can see that every single element is real. We've seen previously that the complex conjugate of a real number is just that real number, nothing changes. You can also see visually that this is going to be a symmetric matrix. So if you put this here to make it clear, you can see the 2 and 2, the 3 and the 3, the 5 and the 5, it's symmetrical about its leading diagonal. So we've got a symmetric matrix. By definition, a matrix is symmetric if your matrix A is equal to its transpose. So we've basically shown that the two conditions for being Hermitian are satisfied. We've got the original matrix, you find the complex conjugate, then you find the transpose. So the complex conjugate transpose is exactly the same as the matrix. So we can say that A's complex conjugate transpose is the same as A. And so A Hermitian, so the complex conjugate transpose of A, it's all the same. This matrix, therefore, is Hermitian. So every single real symmetric matrix is always going to be Hermitian. So that's a really quick way to check. Another super useful property that you should know is that Hermitian matrices always have real eigenvalues, and that's a nice thing to keep in your head, and it helps you make sure that you're getting the right answer and you know what to expect. So I hope this video was helpful to you, and you now know exactly what is meant by a Hermitian matrix. If this video was helpful to you, please subscribe below. And finally, thank you very much for watching.